Welcome back to CE439. Today, we're gonna learn a new chapter, Chapter 6, Rock Excavating and Drilling. Let's see what are the learning objectives. Number 1, understand the different types of drilling equipment. Number 2, appreciate the factors that influence the rates of drilling rock. Number 3, ability to prepare a rock drilling production estimate. We will not cover Section 6.1 of your text in this class. I will not ask test questions on the material of this section. If you wish, you can review this section on your own for background information. Section 2, Types of Drills. The types of drilling equipment typically used in construction and quarrying operations include the following. Number 1, percussion drills. Number 2, rotary drills. Number 3, rotary percussion drills. This is a combination of type 1 and type 2. Finally, downhole drills are another type of commonly used drills. This type of drill can provide the functions of each of the first 3 drill types. First, let's learn about percussion drills. Percussion drills penetrate rock by impact action alone. The bits of these drills rotate to assist in cleaning the hole and to provide a fresh surface for each impact. The rotation is made on the upstroke only, so no cutting is accomplished during rotation. There is a wide range of percussion-type drills. Handheld drills, which are also known as jackhammers, are one of the most popular type of percussion drill. In this picture, a worker is using a jackhammer drill to remove a portion of the pavement surface. Drifters are larger than jackhammer. Due to the heavy weight, it is mounted on a supporting frame. The supporting frame can be a leg or jack leg. For larger drills, a strong steel frame would be needed to provide extra support. Wagon-mounted drills are another common type of drills. Wagon-mounted drill are basically large drifter drills. It is mounted on wheels to enable mobility from one place to another. Finally, track-mounted drills are also a common type of percussion drills. Track drills are typically large drifter drills. They are mounted on a track crawler. This helps the vehicle to move by itself. The track enables the equipment to access sites with poor condition. Drills can be attached to a hydraulic excavator when extended reach is needed. Percussion drills can be top hammer or downhole drills. Let's watch the following 2 videos to distinguish between top hammer and downhole drills. top hammer percussion drill include the following components: a drifter or drifter drill, a striking bar or shank, couplings, a drill steel, and bits. The figure here illustrates the components of a top hammer drill. The blue block here is a drifter, which serves a hammer to generate the impact force. The striking bar is an extended part from the drifter. Let's have a section cut to have a better view of where the striking bar is located in. In addition, there is a coupling that connects the striking bar with the drill steel. Finally, a bit is attached at the end. Top hammer percussion drills can either be pneumatic or hydraulic. A pneumatic hammer is operated by compressed air, while hydraulic is operated by hydraulic fluid. In addition to top hammer drills, we also have downhole percussion, aka DTH is one example of downhole hammer. Unlike top hammer drill, hammer device of a downhole drill is placed in the bottom of the hole, right above the drill bit. The hammer goes down the hole as the bit progresses. Since the hammer energy is directly transferred to the pit, it has less energy loss. Also, it has a lower noise level than top hammer drills. However, this type of percussion drill can only apply for large diameter holes. The figure in the bottom right corner illustrates the downhole percussion drill. Let's have a section cut of it. And this is the bottom hammer. This picture shows a real downhole percussion drill. As you can see, it is relatively large. In addition to percussion drills, we also have rotary drills. Rotary drills cut by turning a bit under pressure against the rock face. The following are several important notes about rotary drills. Number 1. Rotary drills tend to be used for larger diameters, up to 6 feet, and deeper holes than percussion drills. Rotary drill machines are typically much larger than percussion. Number 2. Rotary drills typically are used in large quarry operations. Number 3. Large downhole hammer percussions may also be mounted on large machines, like rotary drills. What we see in this picture is a large caterpillar rotary drill. As I said, it is commonly used for large quarry production. Let's watch the following video on how rotary drill works. Rotary drills are also used in coring operations. For coring operation, a material core will be collected after the drilling is complete. Another type of drill is rotary percussion. This drill combines rotary and percussion cutting. It can penetrate rock several times faster than a comparable percussion drill. Section F, Typical Characteristics of Rock Drilling. Table 6.2 in your textbook provides typical characteristics of rock drilling equipment. It gives the maximum diameter and depth for different types of drills. As you can see, rotary drills are typically used for larger and deeper drillings. To find drilling rates, you can use Table 6.3 in your textbook. This table provides how many feet a certain type of drill can do in an hour. Section 3, Drill Bits. There are a variety of types of drill bits. You can see Figure 610, page 98 in your textbook for some primary types of drill bits. As you can see here, the primary types of bits include A. Cross-type bits, B. Button bits, C. Diamond core bits, and D. Roller bits. For percussion drilling, we use cross-type, also known as X-type bits, as shown in this figure. The drilling edges of the bit are usually tungsten carbide, embedded in steel. We also use button bits for percussion drilling. The figure below illustrates a button bit. It is good for a wide range of drilling applications, including hard and soft materials. It has higher penetration rates than cross bits, and it is less likely to jam in a hole. This is a comparison between a new bit and a used one. As shown in the right figure, the buttons on the used bit is worn off. This will reduce the drilling efficiency. For rotary drilling, roller bits, also known as trichome bits, are typically used. It can drill very large diameter and very deep holes. This figure shows two roller bits with different diameters. The bigger one is about 26 inches. For rotary percussion drilling, we typically use trichome bits that are modified to withstand the additional stress and strain of the impact load. Some bits used for rotary percussion drills are similar to X-type bits, but may utilize special designs for the cutting edges. Here are some popular trichome bits used for rotary percussion drilling. We got Atlas Copco Trichome, Atlas Copco Pard, and VAR LRP. For rotary drilling, sometimes we use coring bits if we need to collect a material sample. This type of bit uses diamonds or chilled steel shot to penetrate rock. As noted earlier, this bit is used when we want to collect the material from the drilling. A rock core inside the bit will be extracted after the drilling is complete. Section 4, Drilling Patterns and Rock Yield. Please note that drilling is typically done for the purpose of blasting rock. There are a number of factors that determine rock blasting production. These factors include: Number 1, hole size or diameter. Number 2, hole depth. Number 3, hole spacing. Number 4, type and amount of explosive in each hole. Finally, the type and soundness of the rock being blasted. This figure shows a pattern of drilling holes, which are used for rock blasting. Let's learn some terminologies related to drilling. The figure on the right side here shows a certain rock bench. To excavate this rock block, explosive will be put into these deep holes. Here are key parameters of the drilling work. Burden B is the distance from the open surface to edge of the nearest hole. Spacing S is the distance from center to center between two adjacent holes. Subdrilling J, this indicates portion of the hole, which goes deeper than the bench floor. H is the height of the bench. Finally, L is the total length of the blast hole. Please note that your text does not include all of the terminology discussed earlier. Of those terminologies, the burden and spacing distances determine what is known as the drilling or blasting pattern. This is a plan view of the rock bench to be excavated. Burden is the distance between the rock face and the nearest row of blast holes. Burden also indicates the distance between two rows. Spacing also indicates the distance between holes, but it is the distance between holes in the direction along the open rock face. While the burden and spacing are not required to be equal, your textbook assumes equal burden and spacing. Table 6.4 in your text provides typical drill patterns, assuming equal burden and spacing distances for various hole diameters. Using this table, given the hole diameter and the rock type, you can find the distance in feet between holes when they are in a rectangular pattern. Another important note, your text uses the term effective hole depth for the bench height H. Again, the bench height H is typical term used in practices. However, your textbook uses the term effective hole depth. The two most common drilling or blasting patterns typically used are rectangular and staggered, which are shown in figure 6.11. Of those patterns, rectangular is the most common. The figure on the left shows an array of blasting holes in a rectangular pattern, while the right figure illustrates blasting holes with a staggered pattern. For the purpose of cost estimating, we may need to know rock production. We can estimate the rock production per hole using equation 6.2, as shown here. In this equation, the production is measured in the total volume of rock in cubic yards to be excavated per drilling hole. S is pattern spacing. H is the effective hole depth in feet, typically equal 90% of drilling depth. Note that both S and H are measured in feet. When you multiply S squared by H, you got the total volume of the area covered by a hole. To convert cubic feet to cubic yard, you divide the volume by 27. When B is not equal S, you need to apply this general equation when estimating production. The total volume per hole is equal B times S and H and divided by 27. This figure illustrates the volume covered by a drilling hole. Given a pattern with spacing S and burden B, each hole will cover a half of the rock area between the holes in both directions. So, dimensions of the area covered by each hole will be S by B. If you multiply this area by the bench height, H, you get the total volume per hole. You can calculate the production in cubic yard per foot of the drilling depth. To calculate it, you divide the production per hole by the length L of the hole. Let's do a quick example here. The blasting pattern shown in the figure here. It has the burden of 10 feet and the spacing of 12 feet. You need to calculate the production in cubic yards per hole and per linear feet of drilling if the hole depth is 20 feet. In this example, the effective depth or the bench height is not given yet, but we know the length of the hole, which is 20 feet. As noted earlier, the bench height is typically equal 90% of the length of the hole. Let's use H equal 90% of 20 feet. Now, let's calculate production in cubic yards per hole using this equation here. In this example, burden B is 10 feet, spacing S is 12 feet, and bench height is 0.9 times 20 feet. Next, you need to divide everything by 27, then you got 80 cubic yards per hole as the unit production. To convert the production into cubic yards per linear foot of drilling, you divide the production per hole, 80 cubic yards, by the total length, 20 feet. The result is 4 cubic yards per foot. This is the end of this lesson. Please complete the homework problems listed at the end of your notes. Goodbye for now, and see you next time.